Hi, in this video we're going to be talking about eigenbases. Now eigenbases I've talked about before, but here's the definition written down. So if A is an n by n matrix, then an eigenbasis corresponding to A is a basis for Rn which only contains eigenvectors of A. Okay, just to note, instead of A we could have a transformation T, and the transformation T would need to be from, say, a vector space V to itself. So T goes from V to V, and we could have an eigenbasis for that, which would be a basis for V, which only contains eigenvectors of T. So that works just as well. I'm just stating things in terms of matrices for now. So we have this theorem here. An n by n matrix A is diagonalizable if and only if there exists an eigenbasis corresponding to A. So this if and only if is a two-way implication. So let's just talk about the forward implication. Suppose we have A is diagonalizable. So in other words, there exists a P and a D so that A is equal to P, D, P inverse. And D is diagonal and P is invertible. Now if we have this, then D must be the set of eigenvalues for A. Because A and D are similar to each other, they must have the same set of eigenvalues, and the eigenvalues of a diagonal matrix are the entries in the diagonal. Okay, so A and D have to have the same eigenvalues, and the process of transferring to a similar matrix, such as D, is switching a basis. So the fact that we have this invertible P means that we are switching to this basis made up of the columns of P, doing the diagonal transformation, and then switching back into the standard basis. And because it is a diagonal matrix, it must be that the columns of P are eigenvectors of A. Otherwise, the matrix wouldn't be diagonal. So now let's talk about the other direction. Let's suppose that there exists an eigenbasis corresponding to A. Well, if we have this eigenbasis, then we must also have the corresponding eigenvalues, and we can put those eigenvalues in the diagonal matrix D, and we can put the eigenbasis, all those eigenvectors, into a matrix P as the columns of P, and then because it's a basis, that matrix P will be invertible, and we have all of the components to say that A is diagonalizable. There exists that P and the D. In a previous video, we saw an example of a shear matrix which did not have an eigenbasis corresponding to it. And in that case, we said that that matrix was not diagonalizable. Okay? So recall that the eigenvalues for that matrix were 1 with multiplicity 2. Okay? And this theorem right here says that if we actually had different eigenvalues, then that couldn't have happened. Okay? So let A be an n by n matrix. If we have k eigenvectors corresponding to these k distinct, they have to be distinct, eigenvalues, then the set v1 through vk has to be linearly independent. So that leads immediately to this theorem right here. If an n by n matrix has n distinct eigenvalues, well, each of those is going to correspond to its own eigenvector, and then we have n of them. They're all linearly independent because all of their corresponding eigenvalues are distinct, and therefore they form a basis. Okay? And a basis of eigenvectors is exactly what we need to say that A is diagonalizable. Okay? So in the case where we have n distinct eigenvalues, and I should really say real eigenvalues here, just because we're not talking about the complex case yet. So if we have n distinct eigenvalues, then it's diagonalizable. So I skipped over the proof of this, and now I'm going to go back to that. But before I get there, we need to recall a fact about linear dependence. And let me just fix this here. I should say dependent. So if this set is linearly dependent, then there is some index such that vi can be written as a linear combination of the vectors that came before it. So we know that there is some vector that can be written as a linear combination of the other ones, but this specifically says that some vector can be written as a linear combination of the ones strictly before it in this ordered list of vectors. So we don't need the later vectors. All right, now I want to prove this theorem here. Before I do that, I just want to point out this statement is true as long as you consider the empty sum, the sum of no things. For example, if I is 1, then there's nothing over here. That sum would just be the 0 vector. So if v1 is the 0 vector, then it is written as the sum of some terms that came before it. However, we just want to avoid this case, and in our set of v1 through vk that we're going to be looking at, none of these will be 0 because eigenvectors aren't allowed to be the 0 vector. So I'm going to change this a little bit to say v1's not allowed to be 0. And when I do that, then specifically this index I is not allowed to be 1 anymore. Or I don't have to allow it to be 1 anymore. So, on to the proof. I'm going to assume that we have this set up. So we have a matrix A that's n by n. We have k eigenvectors corresponding to these k distinct eigenvalues. And we're trying to show that this set, v1 through vk, is linearly independent. So I'm going to go for a contradiction here and suppose that this set is actually linearly dependent and try to find something wrong with this situation. Okay? So I'm allowed to use this index I here so that this vector vi is a linear combination of the vectors that came before it on the list. And I'm specifically going to let I be the smallest such index so that is the case. So I know that 1 exists because of this, and more might exist. Like there could be 5 different indices in here so that I could write those 5 vectors as the sum of terms that came before it, or as a linear combination of terms that came before it. And of those 5, I'm going to pick the smallest one. Right? I can, if there's a bunch of them, I can always pick which one's the smallest. Okay. So I have this smallest one, and I'm going to now take this equation right here, and I'm going to apply A to both sides. So I have this matrix A, I'm going to apply it to both sides and see what I get. So AVI is A times this stuff. Okay. So I know that A times VI is the same thing as lambda I times VI. And I know that A applied to this linear combination is the same thing as the linear combination of A applied to the individual vectors. So I'm just using the linearity of the map A to distribute it in pull out the constants. Okay, and now I'm going to do the same thing I did over here by saying these are all eigenvectors, so let's just use the fact that A times the eigenvector is the eigenvalue times the eigenvector. Okay, and while I'm at it, I'm also going to do something else. So let's just do that on the right side, and I'll do something else on the left side. So this is C1 times lambda 1 V1 all the way up through Ci minus 1 times lambda I minus 1 Vi minus 1. Okay. On the left side here, I have lambda I times Vi. I'm now going to remember that Vi is this linear combination here, and I'm going to replace Vi by that. All right. I'm now going to move everything to one side of the equation and group some like terms together. So to start out with, move everything to the left side, and I'm going to count how many V1s I have. So V1 is going to have a coefficient, which is lambda I times C1 coming from this side, and then minus the coefficient over here. So minus C1 times lambda 1. So lambda I C1 minus lambda 1 C1. Okay. And now looking at the last term, well, we have lambda I times Ci minus 1 and then minus, over here, the coefficient is lambda I minus 1 Ci minus 1. So all the coefficients look like this. Lambda I times C sub whatever minus lambda sub whatever C sub whatever. Okay, so these two C's will always be the same, and I can think about factoring that out. Okay, and since I subtracted everything to the left side, what's left on the right side is just the zero vector. Okay, so one important thing to note here is this is a linear combination of just the vectors v1 through vi minus 1. And these vectors must be linearly independent. Remember, even though I'm assuming this whole set is linearly dependent, because I've picked the smallest index I here, the set of vectors I have that I'm using on the right-hand side must be linearly independent. Because, a sub-contradiction argument here is that if these were linearly dependent, if v1 through vi minus 1 were linearly dependent, well then I would have this property again. Any subset of linearly dependent vectors would have some I, so that v sub I could be written as a linear combination of the terms before it. But if I had that for just these vectors here, then that would be an example of an index I that's smaller than the I that I've chosen here, so that its vi is written as a linear combination of the terms that came before it. And I know that can't happen because I have the smallest one, right? So there can't be a smaller one. Therefore, these vectors, v1 through vi minus 1, must be linearly independent. Okay? Well, since they're linearly independent, I have a linear combination of them equaling 0. Therefore, each of these terms, which are the coefficients, must be 0. So each of those coefficients must be 0. And I'm going to factor out these c sub whatevers from each of these terms. So this one is ci times lambda I minus lambda 1. That's got to be 0 all the way up through ci minus 1 times lambda I minus lambda I minus 1. That also has to be 0. Okay, so I know that this product must be 0, so at least one of these two terms has to be 0. So either C1 is 0 or this is 0, this difference here. But that difference is not allowed to be 0 because what would it mean for lambda I minus lambda 1 to be 0? Lambda I would have to be equal to lambda 1, and my eigenvalues are distinct, so lambda I is not allowed to equal lambda 1. Okay. Similarly, up here we have lambda I is not allowed to be lambda I minus 1. All of the parentheses that I'm getting in all these terms, they're not allowed to be 0. Okay? So when I say the product of c sub whatever times parentheses equals 0, what I'm really saying is the ci's must be 0. So C1 must be 0. C2 must be 0, C3 must be 0, all the way up through Ci minus 1. Okay, so I've just said that all of these Ci's are 0. And remember, the thing that defined the Ci's originally was saying that Vi was equal to this linear combination where the coefficients are the Ci's, or the C whatevers. And I'm saying that all the coefficients are 0, therefore Vi is 0. Right? Vi is 0 times V1 plus 0 times V2, all the way up through 0 times Vi minus 1. So what this is saying, sorry I'm running out of space here, is that Vi is equal to the 0 vector. Remember, I was looking for something that didn't work for this, for a contradiction, and right now I'm saying that all of this stuff implies that my ith eigenvector is the 0 vector. None of the eigenvectors are allowed to be 0. So this is a contradiction, which means we're done with the proof. Now I want to talk about an important theorem dealing with diagonalizability. So this theorem is Theorem 7 from section 5.3 in the book, and it tells us basically the classification for when a matrix is diagonalizable in terms of some fairly tangible things. So I've decided to reword this, and to start out with, we're going to look at a definition. So I've been talking about the multiplicity of a root, and what I've been meaning so far is the algebraic multiplicity. If you take the characteristic polynomial and look at the multiplicity of some particular root lambda I, that is called the algebraic multiplicity. Okay? And we can denote it m sub a of lambda I. The purpose for giving this notation is just for the theorem that's about to come. You don't need to memorize this notation. Another type of multiplicity that we could talk about is the dimension of the lambda I eigenspace. And this is called the geometric multiplicity. So one's algebraic because it comes from the polynomial, and the other one's geometric. It is the dimension of the lambda I eigenspace. Okay, and it has this notation. So now we're going to take an n by n matrix, and I'm listing off the eigenvalues right here. So lambda 1 through lambda k. So k is definitely less than or equal to n. An n by n matrix can't have more than n eigenvalues, but k could definitely be less than n. And we have three things that are true. So the first one is sort of an important fact. You need to find bases for these lambda eigenspaces sometimes. And how do you know what the dimension is before you start? Well, one quick bound on these things says that the geometric multiplicity, the dimension of the eigenspace, has to be less than or equal to the algebraic multiplicity, the multiplicity of the root in the characteristic polynomial. I could also put in here that the geometric multiplicity is at least 1. Okay? Given that lambda I is actually an eigenvalue, then the dimension of the eigenspace has to be at least 1. Otherwise, lambda I wouldn't be an eigenvalue. Okay? So that's the first item. The second item, part B, says A is diagonalizable if and only if I add up all of these geometric multiplicities and I get n. This happens exactly when all of the geometric multiplicities are equal to their corresponding algebraic multiplicities. Okay, so we have this less than or equal to here. If this is always equality for each of the i's, then that's exactly what it means for the matrix that we're talking about to be diagonalizable. If any of the geometric multiplicities is smaller than its corresponding algebraic multiplicity, that's when we have a problem and we won't be able to diagonalize because there won't be enough eigenvectors to form a full basis. Okay, so I should also point out that we might also have a problem not only if the geometric multiplicity is strictly less than the algebraic multiplicity, but also if we have complex eigenvalues, that will also mess us up. Because essentially what that means is our list won't be complete. We'll be left with some irreducible quadratic factors in our characteristic polynomial. And we don't want that. So we're assuming that we have the maximum amount of eigenvalues here that are real, and some of them might be equal, which is what's causing the k to be potentially less than n. We don't want to have some that are complex. Okay, so these are real eigenvalues that we're looking at. Okay, part C says if for each I we get a basis for the lambda I eigenspace, we're going to call that bi, and we already know that A is diagonalizable. And let me just say that having A be diagonalizable is the same thing as having the dimension of bi, which is this, equal to the algebraic multiplicity. So if all of these have the correct size, and we only have real eigenvalues, we don't have any complex eigenvalues, then the union of all of these bases for our lambda I eigenspaces is an eigenbasis. And it will have the correct size because the sum of the dimensions of all these things will be n, and that'll be an eigenbasis corresponding specifically to A. All right, thank you for watching.